Most of the people who are listening to this podcast may remember that one page called, there is no direct experimental evidence of string theory. So he is the author of that page, by the way.
People who are going to dislike string theory based on entirely based on knowing basically nothing about it,
Mhm.
you kind of you shouldn't really worry about what they think. In the sense that there's something we don't understand about DESitter, and there's something we don't
Mhm.
understand about the vacuum energy in our current universe. And that thing we don't understand is the thing we need to find.
Comments by people who don't know anything about string theory, but they are very confident about their opinions of string theory. So, welcome to Phymaths podcast. Today, our guest is Dr. Joseph Conlon. Dr. Joseph Conlon is a theoretical physicist at the University of Oxford. He works on string compactifications, string cosmology, and numerous other areas. And he's also written two books. One of the books is called Why String Theory, and his next book is coming this November, right? If I'm not wrong. The name of that book is Origins, the Universe in Verse. And by the way, I mean, most of the people who are listening to this podcast may remember that one page called, there is no direct experimental evidence of string theory. So he is the author of that page, by the way. So first of all, Dr. Conlon, welcome to the podcast. It's nice to have you.
Thank you,
Um,
Hassan. I'd love to be on it.
so first thing that I want to ask you is that actually I was looking into in your educational career, and I discovered that you did two undergrads. So was there any
Yes.
reason to do two undergrads?
So the first one I did when I was young. So the kind
Hmm.
of so my history is a little unusual here. So I was always good at maths, and so when I was 13, I took my maths A levels, which are the exams that you normally do when you're 18. So I took those when I was 13, and so because I was kind of advanced maths, so what I then did is I did a kind of a part-time maths degree at the local university, which is Reading, while still attending my regular school courses. So then I did so I went to do regular school A levels in kind of physics, chemistry, English, Latin, and some Greek as well. But I was doing this part-time maths degree along it. So basically, then at the age of 18, I had a maths degree which I had done part-time, basically at my local university, alongside my regular school thing. And both for social and scientific reasons, I think it was absolutely the right thing to do to then do a second
Hmm.
undergraduate degree in physics. So then I went to Cambridge to do physics, and I didn't tell anyone there. Well, I didn't tell any of the other students. It had been on my application, but I didn't tell any of the other students that I actually already had an undergraduate degree in maths because
I
I
see.
just wanted to, kind of, to be a normal student, yeah, doing a
Mm.
normal degree and not being like I was at school. I was also the person doing a maths degree on the side.
So was there a transition in your interests from maths to physics in your undergrad? Because you
I
ended up
think I
doing a
think I was
physics
always
degree.
I was always more interested in physics. I always kind of liked physics more than maths. I mean, the really good thing about it's an odd, the really good thing about doing a physics undergraduate degree when you already have a maths one is you can really focus on the concepts that you understand to understand the physics, and you're not simultaneously trying to understand the maths.
Hmm.
So in
I see.
terms of really, being able to get a deep understanding of the physics without having kind of mathematical uncertainties at the same time was definitely a benefit from that, as well as the kind of the social maturity that comes from,
So
from doing it at the ordinary time.
Was there any book or a mentor that actually, sparked your interest in physics?
It kind of runs in the family. So my mum's a physics
Mhm.
teacher, and
Okay.
she really likes physics. She's only just retired. She's kind of well, she retired definitely past the normal retirement age, and so she was head of physics for many years at this a girls grammar in Reading. And my dad has a maths PhD. Um, my uncle's a maths professor. Yeah, I mean, I don't really need to look far to see why I kind of like theoretical
Mm,
physics.
I see. Okay, so you have worked on the problem of cosmological constant, right? So I really want to know your thoughts about the recent study from DESI, which says that the cosmological constant may be dynamical and W is probably not equal to -1. So do you have any thoughts about that study?
Yeah, so I was in the Morion meeting where this thing was okay. So I think you need to okay. So this is I think we should all have a lot of skepticism about this at the moment. So the obvious reason for this is
Mm,
you see how where does this result come from? So what what they're doing is they're measuring what's called the baryon acoustic scale, which is basically these scales of kind of waves of oscillations which come from the early universe and they're kind of imprinted on the galaxies. That there's a certain scale, about 150 megaparsecs today, which is kind of galaxies are roughly more likely to be found separated by that. And what they're doing is they're looking at this scale and how it's behaved across the expansion of the universe. And so they've got a data point for kind of redshift. They've got data points at various redshifts, and they've got different there are different samples of galaxies that are feeding into each data point. So they've got one at redshift. There's a redshift point at 0.5, 0.9, and these various different things, and they've got
mm,
different samples feeding into each one. And you look at where this result is, this kind of preference for varying W is coming from, and it's dominated by this kind of point at redshift 0.5. So what you've really got is you've got something which is driven by not huge significance, driven by pretty much one data point. You've got different samples for each one of the things. They only get the results when they combine lots of different things. They have to combine their own results with the supernova results, for example, which are coming again a different method of doing things. So given that the significance is relatively low and
I
it's
see.
coming from combining lots of things, I mean, I think at the moment we should all be a bit skeptical.
So,
I mean,
so do you think that?
a bit
Yeah,
skeptical that this is some fundamental rewriting of cosmology.
yeah, of course. But do you think that suppose that if in the future there are similar results from other methods, then we should give some credence to these results?
Yeah, so it's like the longer you're the longer you're in the subject, the more you see two or three sigma results come along and then disappear. And
Mhm.
obviously, if occasionally one of these two or three sigma results turns into 5 sigma, turns into 8 sigma, turns into a nailed-on truth about the universe, then
Mhm.
the people who find the 2 or 3 sigma thing is where you go back and say, yes, this was the first sign of something
Right.
incredible. But most of the time, those 2 or 3 sigma things go away.
I remember that in April 2020, there was this study that said the universe is probably not isotropic. And a lot of people were jumping on that bandwagon. But as you were saying, that thing actually went away because it was not 5 sigma. So yeah, I think you're right about that. Um, okay, so one thing that I want to talk about, I think that's probably the main part of the podcast, is the whole field of string compactifications.
Yeah.
So string compactifications, as you surely know, that in the 2000s, it was a very booming field, and a lot of work was done on that particular field. But why people are not able to get, something like deSitter space-time until now? Do you think that there is some fundamental problem that we need to solve to get something like that, or do you think that there is something else that we are missing?
Okay, so I think we should separate things out a little bit. So there's the question of
Hmm.
deSitter by itself, and
Hmm.
there's the question of the exceedingly small cosmological constant, which is smaller than kind of all the other scales.
Hmm.
Now, so deSitter by itself, so when you think about compactifications, there are kind of clear reasons why deSitter by itself should not be easy to get. And the kind of difference between deSitter and ADS is roughly, it sounds, with ADS, you only really need two terms to contribute to give you ADS because you just come down below zero and then you go back above. Whereas deSitter, you have to go down, then you have to go up, then you have to go down again in the potential. And so you need kind of more things balancing, more things feeding in. So then it's obvious that deSitter is going to has to be more complex at a technical level. And then there are these kind of various proposed constructions bringing together various ingredients to make deSitter. And my personal view on them is that they're not obviously wrong, but they are not obviously right either. And by this I mean that there may be deep properties about deSitter space in quantum gravity that we are missing or that we do not fully understand. And my personal belief is that there is something deep we do not understand about the cosmological constant, about that there's some deep principle we're kind of missing, and there's something we're missing. And this might tie both to actually the nature of deSitter in the first place, and also to why you could have a apparent vacuum energy that is so much smaller than all the other scales in physics.
Right. So one thing that a lot of people are trying to do is something called moduli stabilization, which means that these extra particles that we get when we do compactifications, they're trying to make them massive so that we don't have new long-range forces. But what do you think about this approach that some people, I don't know if they're doing it today or not, but they certainly did that in the past, that they were saying that probably equivalence principle is not entirely true. I mean, there are some long-range forces that interact very, very weakly. So probably we don't need to do moduli stabilization. So what do you think about that?
I haven't really heard that. I mean, that seems an odd.
I think it's in Polchinski's review on cosmological constant. I mean, he just mentions that at the passing.
I mean, so the difficulty with if you have, because the difficulty is if you have moduli that are exceedingly light, they do not have masses, then they should roll, because once they are, if they are lighter than the Hubble scale, then sorry, if they are light, then you expect them to have evolved at some point in the course of the universe. And because, for example, all the couplings in string theory also tie to the kind of webs of the moduli. So then you would again be expecting that couplings to have varied in the past, and there's no evidence for that. So you would have the problem of kind of, well, why don't you have fifth forces? Why don't you have varying couplings? Why don't you have, if things genuinely are exceedingly light, why aren't all the other scales exceedingly light as well? And so I don't personally think there are any really kind of good scenarios where the normal moduli can be basically massless. I mean, you can do it with axions, but axions are different because axions have restrictions on their interactions. They have restrictions on kind of derivative interactions. So all interactions of axions are suppressed by powers of momenta, which means you can have axions naturally light and they not cause a problem. But with the other moduli, I think it's very hard to do.
I see. And what do you think about the approach that some people are trying nowadays, which says that deSitter may not be the vacuum, it may be one of the excited states?
I think everyone would basically say that deSitter is not an absolute vacuum. That even if the normal thing of saying that you're in a deSitter minimum would be that that's not the absolute vacuum. That in principle you could tunnel away from that to, for example, Minkowski space. I mean, there are ideas of kind of quintessence where you have rolling fields, but they tend to have similar technical problems to this question of how do you get the fields extremely light. I mean, it's not a problem getting extremely small scales by themselves, but the problem is always when you try and say that the Higgs mass is 125 JeV, the top quark is 170 JeV, and you're going to have a natural cosmological constant at 10 to the minus 3 electron volts, or something, or anything quintessence, anything mimicking a cosmological constant.
I see. And I'm sure you also know about this one that there are a lot of people actually, I don't know if it is a lot of people, but some people at least say that the true vacuum, as I said before, is probably ADS, and there is some ADS bubble coming for us, and so something like the Coleman-DeLucia, tunneling is going to happen in the future. So what are your thoughts about that thing? I mean, it's related to the fact that deSitter is probably not the absolute vacuum, right?
Yeah, so there might be stuff we don't understand about deSitter, but otherwise this would seem naively likely to be true. But yeah, if the tunneling lifetime is something that is like e to the minus 10 to the 120 years or some enormously, sorry, e to the plus 10 to the 120 years, then it's not really something we need to worry about as a phenomenological problem.
Right. And I think one more question that I have about deSitter is that what do you think about deSitter's swampland conjecture? I mean, we don't have a lot of confidence in that, but what are your thoughts about that?
So by the deSitter swampland conjecture, you mean basically that deSitter doesn't exist as a kind of yeah.
Right. I mean, it makes it a bit more quantitative, but essentially it's saying that what you think.
Yes. Okay. So some of the swampland conjectures, like the distance conjecture, there are ones which I think have kind of more support. I mean, I think the thing about the kind of, that deSitter might not be a true state of quantum gravity, might not exist in quantum gravity. I mean, this idea goes back a long time, and it might be the case, but this comes back to the sense that there's something we don't understand about deSitter, and there's something we don't understand about the vacuum energy in our current universe. And that thing we don't understand is the thing we need to find. So it might be the case, there might be deep principles of quantum gravity that forbid you having deSitter vacua, but but then one needs to kind of say what they are. I mean, sure, you can say, well, maybe deSitter exists, maybe deSitter doesn't exist, but unless we actually get what those deep principles are.
I see. A lot of people, are trying some non-supersymmetric approaches because a lot of scenarios that people work with are supersymmetric. I mean, as you surely know that in supersymmetric cases we have a lot more control on the calculation. So one approach that some people try is there is this heterotic theory which is non-supersymmetric and free of tachyons. So some people are actually trying to get deSitter in that particular theory because we do have non-supersymmetric case there. So that's one example. But do you think that to find deSitter, we will probably need to leave supersymmetry? Because I mean, supersymmetry is more like a comfort zone for a lot of researchers.
Yeah, well, so things like modular stabilization, things like LVS, the large volume scenario, which I wouldn't. That's
Mhm.
not that's a non-supersymmetric vacuum that breaks
Mhm.
supersymmetry in the vacuum. As a starting point for something that you would then lift up to deSitter, that starts off with something non-supersymmetric. So I don't see any particular need we would need to be. We know that deSitter can't maintain supersymmetry, but there's no reason we should be starting with something that's supersymmetric either. I mean, the world breaks supersymmetry.
I see. And there's this idea called holographic moduli stabilization, where they use, CFTs to put some constraints on, different moduli stabilization scenarios. And there are some interesting directions that, have emerged in that particular approach. So do you think that it may happen that to finally solve the problems in moduli stabilization, the holographic moduli stabilization will give us a significant, role?
Well, this is something I've kind of worked on quite a bit over the last few years. I mean,
Hmm.
these are
Yeah.
if you have what did I say about them? What would their holographic jewel be? And I think that, there is some very interesting because the interesting kind of the modular stabilization scenarios often would, if they are really there and they're really ADS, would correspond to scale separated CFTs. So these are conformal field theories where there is a large hierarchy in the size of the dimensions of the various operators. And so this is kind of there's a CFT question, which is because such things will be very rare in CFT if they exist. So they think, what would be the nature of these? And so we found some very interesting things that, for example, DJKT, which is one of these
Mm.
type 2A modular stabilization constructions. So this would have integer conformal dimensions, for example. So it'd be
Mhm.
a very kind of more or less unique, quite striking properties to such a dual conformal field theory. And I think these are hinting at something, but unfortunately, I can't
Mhm.
exactly what they are hinting at.
So, do you have any ideas for some future works that someone can do in in this particular direction using holographic model stabilization? Because this seems an interesting approach.
Yeah, I think one thing it's quite hard to just pick concrete projects. I mean, there are some part-time subjects, areas of the field where you can just it's quite easy to say this is the concrete project, this is the concrete calculation you could ask a graduate student to do to do. Where
Mhm.
there's a clear set of things, you turn the handle, you will clearly get a result. So with this question of how would you holographically describe modular stabilization scenarios? I think it's a very interesting question, and I don't think it's one which emits kind of obvious calculations where there's a clear project you can do that will clearly make progress, where you just need to kind of calculate carefully and you'll get it done.
I see.
So
And please go on.
no, go on.
Oh, well, I was going to say that a lot of people have worked on, Calabi-Yau compactifications of string theory because, I mean, first of all, when you work with Calabi-Yau manifolds, since they are complex manifolds, there are a lot of techniques that you can use from, the mathematics of complex manifolds. But if you compare that to the compactifications of M theory on something like G2 manifolds. Uh, Working with G2 manifolds is much, correct me if I'm wrong, but I think working with G2 manifolds is much more harder as compared to working with Calabi-Yau because they're not complex. And we also, correct me if I'm wrong, but I don't think that we have an example of a compact G2 manifold with singularities, and we do need singularities to get non-abelian theories. So do you think that in the future, this particular approach can actually pick up and that may give us some results that we were not getting in the Calabi-Yau compactifications?
Possibly, yeah, because you lack the complex. So possibly there are things you would get from that you don't get from Calabi-Yaus. I think it does depend on what you are aiming at.
Mhm.
In the sense that some of the physics, I mean, I think some of the interesting physics on compactifications, these questions of kind of scale separation and hierarchies. The question is, do you have qualitatively new mechanisms for getting these? Because if you have just the same mechanism operative in a different geometry, perhaps you don't learn so much, or perhaps you don't learn anything particularly, especially new that is interesting. But if you can find qualitatively new mechanisms, then I think then you're really in business.
I see. Okay, so you have also worked on string cosmology, and one of the major problems that one deals with string cosmology is to embed inflation in string theory. Uh, but what I want to ask is that so this is something that I know very little about. But do you know if there are some other if you look at inflation, there are some competing models for inflation, like bouncing cosmology. Do you know that if somebody has tried to embed something like bouncing cosmology in string theory?
Well, I think bouncing cosmology, I mean, it originally was sort of string inspired, I think, originally, because originally it was about, brains that were coming together and then expanding out again. So I think that's where it came from in the first place. I mean, I think the difficulty with bouncing cosmology is there's this thing that you ideate before, you start off well before the bounce. And then the point of the bounce is kind of where the brains are coming together or the strings are reaching stringy sizes. So there's a thing of whether you can really control what happens in that epoch of the bounce. So I think that's the kind of question that always sort of hung over bouncing cosmologies.
So when I say bouncing cosmology, actually, what I mean is more like a Steinhardt-Turok model, something like that.
Yeah. I mean, that's what that came out of like heterotic M theory, the idea of brains that
Hmm.
were coming together and then colliding and then
I see.
coming apart. Yeah.
Okay, so you're saying that there are so it means that it is easy to embed bouncing cosmology in string theory as well.
Well, I'd say it's string inspired rather than
Hmm.
string embedded.
Okay,
But I mean,
I
they're
see, I see,
definitely where did it first come from? It comes from things which are quite close, ideas which are quite closely related to string theory.
I see, I see. Okay, so now I want to talk about your book and your upcoming book, and actually more broadly, I want to talk about science popularization, which your book is a part of. So first of all, as I mentioned before in the podcast, that you wrote this book named Why String Theory, which is, I have to say, which is a very good book, and it came in 2016. Um, but the first thing that I want to ask is that, as you surely know, that there is this one page from that book which says there is no direct experimental evidence of string theory. And the thing is that a lot of people know that page. They may not know about your book, but they know that page. So how does that make you feel? I mean, that's one page from the book has gone so famous.
Yeah, no, it's kind of fun. Yeah. I don't know whether I mean, it's sort of funny in some ways. I mean, I think the thing is, people who are going to dislike string theory based on entirely based on knowing basically nothing about it,
Hmm.
you kind of you shouldn't really worry about what they think, because if someone's going to just take a view on someone who knows nothing about physics is going to take a view on quantum gravity because well then they're just going to take it. I mean, why if you obsess about what such people think about, or then you just, it's not a healthy attitude to do. And but if anyone engages on a more substantial level with the book, then as lots of people have done, I mean, then you will find the kind of the what is a long form coherent defense of string theory as by far the most promising approach to quantum gravity we have, and also just an extremely deep and fertile source of ideas across theoretical physics. But that said,
Hmm.
I mean, it is also important to be true, to be honest, and say that we don't, in terms of what is the direct experimental evidence we have of string theory, there is none. And because sometimes you see there is a sort of like hype that goes on in the media, or people put out dodgy press releases, or their universities put out dodgy press releases, and then they get amplified, and then you see these headlines about kind of like tests of string theory or something. And it's important to be honest and say, we don't have direct experimental evidence that the string theories are correct. The evidence for it, which I think is substantial, is kind of theoretical evidence. It's kind of conceptual evidence. It's about just how intellectually rich this subject is and how much it gives to so much different areas of theoretical physics and mathematics.
Well, I was thinking one day that since this page has gone so famous, if you had written on that page that there is no direct experimental evidence for string theory, and then you had this bracket which says that and quantum gravity in general, that would have been great actually. Because the thing is that, as you surely know, that a lot of people don't realize that string theory don't have experimental evidence because Planck scale is small. It's not a fault of string theory itself, right?
Yeah,
Do you
I mean,
agree?
yeah, absolutely. Because the thing is, if you just think about what's meant by the Planck scale, then the
Mhm.
difficulty is to do definitive experimental tests, you need access to those sorts of energies, and we just don't have them.
Right. So, what led to writing that book? I mean, did you think that there is a need for a book like that? Which I agree there was, but what led you to write that book?
So, I mean, partly it was there's partly a desire to write, partly I mean, if you kind of at this time, there's various kind of quite negative portrayals of string theory. Um,
Hmm.
and I wanted, and some of the things that were used to argue for string theory, I thought was not always entirely accurate, or or was subject to hype, or giving arguments that I, really could not defend. In the sense that if you say, well, string theory is important because extra dimensions might be seen at the LHC, for example,
Hmm.
that was just a bad argument, and it was always a bad argument, and that wasn't the reason for thinking of doing string theory. So, it was a thing to actually just give the honest thing of why string theory. For people who kind of who care who care enough about ideas and physics and questions of quantum gravity to want to engage seriously with these questions, to give the argument of why string theory does have the prominence it does, and that's basically what the book tries to answer.
So that book came in 2016, and as you surely know, that after 2016, well, according to what I think the misinformation about string theory on the internet has actually grown after 2016. So do you think
I think
that
the difference makes on the
there is
internet
an
that everything has grown.
yeah, yeah, of course, but I think one thing that has not grown is the counter narrative to that misinformation, don't you think?
Yeah, I think that's true. I mean, I think the number of people who are willing to write
Hmm.
stuff which is serious and not hype
Hmm.
just gives which gives which respects people to give them the intellectually honest and defense of string theory without trying to kind of fake people with just absurd kind of either absurd levels of hype, or saying things that are just not are not fundamentally honest. Yeah, no, I think I would have I would like to see more of that.
Right. And when I say information on the misinformation on the internet, I primarily mean not in the form of writing, but more in the form of videos. A lot of people are making videos on string theory, which is full of nonsense about string theory. So, uh, according to what I think the counter narrative to that misinformation should be in the form of videos, because I don't think a lot of people read nowadays, which is bad actually, but that's true.
Yeah, well, I'm not the generation for this. Then I mean, I'm not going to be making TikTok videos or
Yeah,
any
of course.
that. So if there is a whole communication about dodgy stuff on theoretical physics through, yeah,
Mm-hmm.
that's not me. It's just not the sort of thing I want to be doing.
Right. I think you have done your part by writing that book. I think someone can convert that book into videos. I'm sure that can be done. But there's one thing that I want to ask is that I have talked about this thing about this misinformation to some string theorists, and they say one thing that kind of agree with. They say that if you look at the early 2000s, and the kind of the popularization of string theory in the early 2000s, they think that that particular popularization actually overpromised about string theory. And this misinformation is kind of like a backlash to that. So do you agree with that?
I think I don't know whether it's particularly I don't know whether it's particularly tied to the early 2000s, but I think yes, I think certainly a
Mhm.
lot of the early popular, yeah, overpromised. And I mean, I think this probably goes back. Probably goes back further, but I would broadly agree with that. Yeah, but I don't think it was just
Mhm.
string theory either, because if you think back to the discourse about the LHC and all the things the LH, the case for the LHC when people were talking about kind of extra dimensions and black holes and strings at a TV, there was a lot of. I mean, this was in a lot of the sort of semi-popular accounts about what the LHC was going to do.
Right. I mean, they were saying
Yeah,
that
no,
you will.
and that was all kind of really that was all over promising, because these were very quite far-fetched scenarios.
Right. I mean, if somebody says that we are going to find supersymmetry in LHC, I think that's not far-fetched. I mean, before LHC started, but finding extra dimensions, I agree that was far-fetched. I mean, because we knew that the Planck scale is very small, right?
Yeah, no, yeah, that's what I mean. Yeah, I think supersymmetry was a reasonable thing to hope to see.
Hmm.
Um, things like evaporating black holes was very very much on the kind of the kind of winning the lottery.
Right, right. So, in your book, Why String Theory, there are a number of criticisms that you have addressed in, I exactly don't remember, probably chapter 11. Uh, and some of the criticisms are, the mainstream criticisms that people have on string theory. So one of them is the background independence thing, and then you have this too many vacua thing, and then to prove that string theory is the right theory non-perturbatively, and then there are a lot of, for example, the um, I don't remember exactly the Einstein equation thing, but the thing is that these were the mainstream criticisms until 2016. So what I want to ask is that have you seen any new criticisms coming out after 2016 that you think they need to be addressed?
I think I think scientifically the main criticisms you would make are still the ones.
Mhm.
I mean, I think you get sometimes get the sort of this is all nonsense. Everyone is just wasting their time. But those don't tend to be a substantive engagement with questions of the Planck scale. Like if you think you should work on problems that are going to deliver humanity in the next 4 years,
Mhm.
then string theory is not going to do that. But that's
Right.
not why you should think about quantum gravity. That's an argument against thinking about quantum gravity. Full stop.
Hmm.
It's a legitimate argument. I mean, someone could say, yeah, no, you just, why care about this stuff? Go and do something practical. Okay, that's a legitimate argument. It applies for all quantum gravity research.
Hmm.
And yeah,
I mean,
I,
people were saying
I
the same thing about quantum mechanics when it was discovered.
yeah. But humanity needs people who want to solve stuff for the next 6 months, and people who want to think about stuff that will come good on much longer timescales. So that's, I think, is more a kind of question of what sort of person you are in terms of what you like to think about or what you're willing to think about.
Right. And as you said before, that in order to criticize string theory, you don't need any background in physics because since I, run a YouTube channel, I get a lot of comments by people who don't know anything about anything about string theory, but they are very confident about their opinions of string theory. And I question myself about this thing that where this confidence is coming from. And when you probe this thing a little bit, it turns out that they're following some people on the internet and they just take whatever they say at face value. And these people are physicists, but they have not worked in string theory. So the thing is that, as you were saying before, that a lot of common people are criticizing string theory without any knowledge of it, and I think that's very, very dangerous. But do you think that there is any way in which this can be countered? I mean, if the thing is that here's the thing: if we just make videos to address the misinformation, do you think that's enough, or do you think that we need to do something more?
It's kind of hard because the number of people with a serious interest in theoretical physics or certainly a serious knowledge of theoretical physics, is always going to be small. And
Hmm.
the idea, you know this cartoon of someone says, "Well, I've seen something wrong on the internet today. I better correct it." If you're going to argue if you're going to argue against disinformation or misinformation on the internet, or just people being wrong on the internet, you'll be arguing forever. But you also need to spend time to build constructive stuff, to do actually deep positive things. And yeah, yeah, that is stuff where you just have to not care at all about what other
Mhm.
people think, and certainly about what random people on the internet think.
Well, I was asking this question because, so I think I've asked this question to two or three guests on my podcast. I'm actually worried that, this public perception of string theory may eventually dry out the funding of string theory, because here's the thing. I mean, as you surely know, that the people who grant the funding, they're not necessarily working in string theory. So how would they know if this is a good thing to work on? So okay, so I think I invited Thomas Van Reet on my podcast, and he actually gave me some anecdotal evidence, not general evidence, but some anecdotal evidence, where he said that he applied for funding regarding some project on holography, and it turned out that when the answer came from that funding agency, they actually rejected the funding proposal, and their response was like a copy paste from these books from Sabine Hossenfelder and Peter Voigt. Don't you think that that's dangerous? That if funding agencies are going to do that?
Yes, certainly they're going to copy and paste from books. I mean, it's always going to be the case that when you ask for money, you're mostly going to be evaluated by
Mhm.
people who are way well outside your field. But what I think, it's not the random stuff on the internet. It's if there are positive and serious and just the honest accounts of why you do string theory and the intellectual value it brings, then people read that, and then they're aware of that. Because I mean, one of the biggest dangers is not really random people on the internet. It's when people who kind of have positions in the subject engage in kind of unsubstantiated hype, because that then they have the profile that means they get read, and other people read them, and people, their colleagues in different areas of physics read them. And if stuff is just hype, most people can normally see through hype, even if they're not in a position to kind of call out publicly that it's hype. And then that does damage, when people subsequently apply for grants, that does damage the subject. Yeah.
I see. Okay, so now I want to talk about your second book, which is coming this November. Its name is Origins, the Cosmos Inverse. So can you tell us about that book, what that book is about?
Yeah, so this is it's an account of the early universe in verse. So it's a slightly mad project, if you like, that it was written over a period of several years, but it is what it said. So it's two long poems about the early universe. One about the origin of the elements, starting
Mhm.
through nucleus and then moving, moving through stars and supernovae, and the other is about the origin of the galaxies through inflation. So the account of cosmological inflation, how that gives rise to the growth of structure in the universe, how this then growth of structure turns into galaxies.
I see. And you
What's
said,
novel is this is it's kind of entirely written in verse rather than in a more the more conventional prose style.
I see. And you said that, this is a project that was in progress for several years. So when did you start this project?
Probably about 5 years ago. I mean, it's something because it's something that's tended to be written on the train as I commute to and from work in the morning, and
Hmm.
then come back in the evening. And so it gets done. It's got done a little bit a day. But if you do even a little bit a day over several years, then it adds up to something substantial.
I
So I
see.
mean, so it's about kind of 2,200 to 2,300 lines. So then plus the notes. So it ends up about 150 pages, and
I see.
it will be out this November.
So since you're a full-time researcher, how do you balance your time in research and writing popular books?
So with the verse, it was easy, because I do it on the train. So like when I'm on the train in the morning into work, I work on it, and then as I get off the station, I stop, and then
Mhm.
on the way back, I start again, and then I stop when I get home. And that rhythm actually work
Okay.
quite well for me.
Okay, but what about when you were writing why string theory? How did you manage your time then?
So it was mostly kind of written, on the in odd bits of time until I kind of the point where I had a contract and about 6 months before I had to think. So then I kind of there was a period of about 6 months where it definitely I was writing it in, as part of my kind of regular work time. And so there's, if you look at my kind of publication list, there's kind of a, the number of papers, there's a kind of dip in 2015 or 2016. And that's
Hmm.
basically the six when I was focusing on finishing the book.
I see. And is it a bit hard when you're writing book about string theory, which is a very technical subject, but you're writing it for the popular audience? Is it hard to not use the jargon? Because sometimes it can be hard. I mean, to convey an idea without using any jargon.
Yes, definitely. I mean, that's all the kind of, that's where where the work lies into trying to
Hmm.
get across what are the real ideas, what is the real idea, but without just kind of, going on, oh, and yeah, the ADS CFT corresponds with n equals 4 super young mills, and these are symmetry, and just dropping into language that people cannot follow at all.
Hmm. I remember that there was this example in chapter 11 of your book, and you were trying to address the criticism that since there is an infinite number of vacua in string landscape, therefore there is an infinite number of four-dimensional physics. And there was this example that you said that where you said that the number of human genome is much larger than 10 to the power 500, but it
Yes,
does not mean that we cannot predict the number of fingers,
yes.
of the person. I think that example was really good. So were there some other examples that you had to come up with in order to, write a book for a popular audience where you, simplified a very complex idea using that example?
Yeah, I think that's something you do. I mean, so like one is also, in terms about like perceiving extra dimensions, like why we can't perceive them. So one example, is the idea of trying to knit wearing boxing gloves. And the idea, if you're wearing boxing gloves, anything on a small scale, you just cannot possibly do if you had boxing gloves on. And it doesn't mean that the
Hmm.
smallest scale doesn't exist or that there can't be structure there. Is you're just not sensitive. You just can't do stuff on that scale.
I see.
And this is another example of, trying to give an example of how extra dimensions could be real. They could have lots of intricate structure, as in a Calabi-Yau,
Hmm.
but we just can't perceive them.
I see. Okay, so your next book, the origins, or origins of the cosmos inverse, is coming in November. Will it be available in the US and UK in November, or will it come in
So
the UK
it's coming out
first?
in the UK. It's coming out in the UK in November. So
Hmm.
it was first of all sold to a UK publisher, and it's currently on submission with US publishers. So I think so in November it's on sale in the UK, but I think if you're in the US, I think you'd have to order it from the UK because it won't be
Okay,
on
I
sale in
see.
the US as kind of a native US publication in November.
So,
Just
so, so do you have any idea of when it will be available in the US?
not because that depends on a publisher being kind of
Okay,
offering to
I see. I understand.
yeah.
I
Yeah.
understand. I understand.
Yeah.
Okay, so I have some questions from the people when I announced this podcast. So I'm gonna ask those questions. So some of these questions can be a little open-ended, but you can make them precise. So this question is from Thomas Van Reet. He said that what is Joe's opinion on the most productive way forward in string theory to make contact with the real world, if possible at all?
So I think cosmology, but so the bias I put on this is, this will obviously relate to what I'm doing research on at the moment, because what I do research on is where I think the most. So for me, cosmology. So there's this long period of the universe, about half the universe on a log scale, between the time of inflation and the time of BBN, and we essentially have no observational constraints on this. And it's also an area where actually, if you think about string theory, there's lots of ways that string theory can really modify what goes on compared to our standard picture of inflation, then radiation dominated. So, for example, you have periods of moduli domination, where the energy density of the universe is 100% in the form of stringy moduli. You can have periods of like conation, where where fields evolve through transplancking distances if we have a long period of inflation. And again, the energy density of the universe is dominantly in like stringy degrees of freedom associated with the moduli of string theory. So this is so for me, this is the area where both it's something that it's a period of our actual universe's history. it's observationally unconstrained, and there's lots of reasons to think that kind of stringy stuff could have happened then. So that for me is it's what I'm thinking on at the moment, which is where my current research is, and but that's also because I think it's an area which is productive for thinking about giving connections to string theory to stuff you can hopefully ultimately measure.
Well, so there's a follow-up question. So there's a follow-up question that I want to ask. So suppose that if we are able to make small black holes on Earth, will that be one of the routes where we can probe quantum gravity more directly?
So I think almost by definition, if we can make small black holes, those black holes are probably like TV, involving things like TV. So, and then they're probably talking about low scale strings. And if you have low scale strings, then you are, instantly in business in terms of making connection in string theory, because you've won the lottery. And if the string scale is 10 TeV, then that's wonderful for doing experiments on string theory. But I think that's in a category of a kind of a lottery ticket.
Right, I agree. Okay, so the next question is that if he had to bet on which prediction of string theory would be observed first, what would he bet on?
Cosmic strings. Because so the one distinctive, the one real, totally stringy stuff. And again, this is slightly a lot of a lottery ticket, but it is the one thing you could feasibly have cosmic superstrings actually in our world, in our universe, as a cosmic superstring network, and this is not ruled out. They could be there today as part of our universe. So this is really the one aspect of kind of stringy strings, as you were, the real string theory, where you could actually have a chance for it to exist really in the universe today, and it could really exist, and actual superstrings could exist in the universe today. So in terms of what's the best chance of seeing something which is absolutely 100% stringy.
Right. But I have one question about that. So I'm sure you know about Nielsen-Olsen strings, right? So if we have something like that in the universe, that's not necessarily superstrings. So
no, but I think of superstrings that could actually have superstrings in the universe, and it's not. I mean, it's probably not likely, but nor is it so ridiculously unlikely.
Well, so you're saying that we could have superstrings. What I'm saying is that if we observe a cosmic string, it's not necessarily superstring, right? Right.
It could be.
Okay. Right. Okay, so the next question is that currently in string theory, the fashion is heavily tilted towards formal theory. What would need to change for this to be no longer the case?
Good question. I mean, okay, so the kind of things change either internally or through external shocks. So the external shock from outside would be something observational, which would then just reconfigure hiring across the whole subject. So in the way that string theory, there were hardly any string theorists in universities until like 1984, and then the kind of Green-Schwarz anomaly calculation resulted in this kind of external shock where suddenly lots of people were hired. So something observational would be the thing that will give the instant change. In terms of longer term things, I mean, I think the things ultimately most string theorists are in physics departments, and ultimately, to defend yourself as a physicist in a physics department over the long term, you have to be able to make the case that what you do matters to the physics department. And so I think, if you over the kind of the longer term, I think if certainly among the people employed in physics departments, it's hard over a long term to sustain having large numbers of people who do stuff which is really looks closer to mathematics or to mathematical physics than to theoretical physics.
I see. So I have another follow-up question on this thing. So you are in Oxford, and in the maths department of Oxford, there is this very well-known group that works on generalized symmetries. So have you ever, thought of working on that field?
I mean, to me, it's a little formal. I mean, in terms of what I think I'm good at and where my kind of interests lie, that if you're looking at a lot of the work on that is in, for example, these things like, if you take 2,0, things like if you take 2,0 theory and you compactify it down to 4 dimensions, yeah, that sort of stuff, and looking at all the kind of the properties you get in that, things like that. That's not really my sort of thing that
Hmm.
is my kind of thing. It's more that's in the more mathematical physics area, and a lot of the stuff on the generalized symmetries, it's that sort of mathematical physics questions, which are not the sort of questions
Hmm.
that
I see.
but particularly what I either kind of particularly enjoy thinking about, or I think I'm particularly good thinking about.
Hmm. I see. So, as you mentioned before, that there were no, significant number of string theorists in universities until that anomaly cancellation thing happened. And in the second superstring revolution, there was this M theory thing. So, can you see what should happen to start a third superstring revolution?
If I knew that,
I
it would
mean,
already
so
be starting. Yeah.
well, so for example,
No,
somebody may
so an
say that,
observational discovery. So suppose there was an observational discovery of cosmic superstrings, for example. That
okay.
would start. Yeah. In terms of the external, in terms of, I mean, I think often the problem is with this is that it's hard to, is that if you're capable of defining on the theoretical side exactly what the result is, that would
Hmm.
be the spark of the revolution, then you're kind of halfway to that revolution already. It's a
Right.
bit like
I mean,
it's a bit like say with ADS-CFT, and someone was going to
mhm,
say, oh, well, what could be the next big thing in 90, and someone said, and if you were able to say, well, I don't, maybe the best is we could have like a rigorous definition of holography such that quantum gravities in ADS space are actually equivalent to conformal field theories. Well, then you've kind of then you've triggered the discovery.
right. I see. So, so it means that you have given two answers. The first answer was the observational evidence for cosmic strings, which is a bit different from the first two revolutions because the first two revolutions were started from a theoretical breakthrough, not an experimental breakthrough. And the second answer that you have given is this definition of holography. Uh, but
No, yeah, so no, I think so. What I mean is that what I'm trying to say is that
Mhm.
something that would clearly trigger a revolution is I can think of as observational things. I can think of and say, well, if this happened, it would have a revolution. On the kind of
Okay.
formal side, I think the problem is if you were able to define what would lead to the revolution, then you've almost
Mhm.
that is the revolution because you can't and once as soon as you define the idea, that's actually the idea that gives you the revolution.
I see. I see.
It's like you can't,
I
you
see.
can't define. It's like this philosophical example about the wheel. Is that
Mhm.
how could you conceive of the wheel before the wheel's invented?
Mhm.
Yeah, who
Yeah.
could say the next discovery we're going to have is the wheel?
Right.
But as soon as you actually define what that is, you've actually made the discovery.
Well, but somebody could have said that we need something that makes us move fast. I mean, okay, that's wheel, but somebody could have said that at least. Okay. Um, the next question is that how far have we come in embedding inflationary scenarios in string theory, including a consistent reheating story and explanation of the post-inflationary state?
So to me, the reheating thing is in string theory is more so the reheating thing is kind of like you say in string theory is probably you have modulus domination and then this reheats. Inflationary models, there's quite a number of inflationary models. To me, again, they fall into this category of not obviously wrong, not obviously right either. That yeah, they've got various moving parts. Um, maybe they could be to do with the real world, maybe not. We don't really know. So yeah, I think we've got. I mean, I think there's lots of ideas, there's lots of models. The models are not bad ones, but we don't know that any of these are actually the or that they
Mhm.
really are true. Yeah.
I see. Okay, so the last question is that which recent developments in string theory should people have their eyes on?
Okay. Okay. So I suppose here. So I think everyone's always slightly biased in this because the nature of it is you work on the things that you think are most important and you think are most interesting. But So let me try and do this where I move away, where I don't answer in terms of the sorts of stuff I work on myself. So I'll try and exclude string pheno just completely from
Okay.
that question. So okay, so by recent, I mean over kind of a number of years, I mean something which hasn't really percolated to the public, I think, is the development in understanding of CFTs,
Okay.
in kind of dimensions other than two. A lot of the stuff that, for example, associated with the kind of bootstrap program has given results which are kind of both nice from a formal side, but also with kind of applications to condensed matter theory and critical points there. And I think this is something that hasn't really particularly percolated into the popular mind at all.
Mm-hmm.
So that's one, that's one thing I will. So yeah, let me just do that one thing. It's something which I think the general people in the public should be more aware of than.
Let's see.
Yeah.
So what kind of questions do you think we should work on in CFTs with more than two dimensions?
So well, the work on that's a different thing, because there, you need to be in the actual area to do the
Right.
work on. But I mean, I think the way but in terms of the way the bootstrap program has kind of classified CFTs, certainly with low central charge. I mean, and the hope one would be is, so one hope which could really give something remarkable will be that a lot of these results are at kind of low central charge. But if you could go to kind of a large central charge, which is in terms of ADS CFT, is what the connection to kind of moduli stabilization and scale separation would be, is that if there was some way to do the bootstrap program for scale separated CFTs, because
Right,
scale
right,
separated
right.
CFTs are ones we don't know whether they exist or not, but are actually extraordinarily significant if they do. And then that also ties into the, coming back to Mike cut string pheno, the question of kind of the moduli stabilization scenarios, that would kind of, and so on. And so that can then tie to the question of hierarchies in physics. So,
I see.
that's an ambitious question of, could you have some analog of the bootstrap program to identify scale separated CFTs in say 3 dimensions with large central charge.
And correct me if I'm wrong, I think we don't know any example of such CFTs, right?
That's right, yes. So that's right. So if there was some way of singling them out or discovering them, that would also be extremely important from a CFT point of view, as well as the connections to kind of string vacuum and moduli stabilization.
I see. Okay, so I think my questions are over. Thank you so much for your time. I hope that, in the future I will invite you again, but thank you so much for your time.